Let us move on to a new topic. This is the early transformations or compiler transformations that are performed on the input to high level synthesis after we have appropriately represented it in some intermediate format. If we have captured it as a CDFG, then we are just calling it a set of CDFG transformations. These are early transformations. They are also called here compiler transformations simply because all of these techniques have something in common with the typical early optimizations that happen in a compiler. Some of them are straightforward, some of them make sense perfectly well in both the contexts, irrespective of whether the output is instructions in a compiler or hardware as it is in synthesis. Some of them are a lot more interesting. Conceptually, they make sense, particularly the later transformations here like unrolling, but many of them are of the simplification variety. The user has provided some input, and the objective of the transformation is to simplify that input in some way. Now, simplification normally should lead to a better quality output, typically irrespective of whether it is a software output or a hardware output. So, that is what these early transformations are about. And even though I say it is mostly independent of the hardware, that is what makes it common with the set of compiler transformations. Some later transformations are actually dependent on some of the other assumptions we are making, like resources that are available to us. The approach that we will take in the discussion of these early transformations is that we will highlight the possibility, where is the opportunity for those kind of transformations. That is what we will identify. We will not necessarily go into too much detail on the algorithms for performing each of those optimizations. As you will see, those optimizations make intuitive sense the moment we illustrate it with an example, but some of them may be not so trivial when it comes to implementation. We will not talk in too much detail about the implementation and the algorithms for doing so, but we will highlight some of the interesting aspects of it. Okay, that is the approach that we will take. Mostly these are illustrations of the possibilities for optimizations, but maybe as part of the project or assignments we could explore one or more of these optimizations. In the class of simplifications, let us start with a compiler transformation called constant folding. It just refers to evaluating constant expressions at compile time as opposed to run time in a software context. Here in the hardware context, what it just means is that you have some expression, there is an opportunity to statically evaluate that expression within our synthesis tool itself, instead of scheduling that operation at runtime, which will cost something. It will cost time, it will cost resources and so on. This simple example should make it obvious. How this subgraph got derived, we are leaving out. It should be sort of obvious what the original HDL statement would have been that led to the creation of a graph like this. As you can see, this is a subgraph. This is not a complete graph. We have for example, for these 3 and 4 we did not create separate nodes. Usually in a graph you do not have an edge without 2 nodes, one at the source and one at the destination. What this typically indicates is that it came from somewhere, maybe this is just part of the graph that we are talking about. So, this is an expression that would have originated from a statement that had these operations, minus C or something like that. right. That is what it came from. Hopefully, it is obvious from the graph, it should be obvious what kind of SDL statement it might have originated from. Anyway, all these behavioral statements need to be addressed in synthesis. We have to create the respective hardware. We illustrate the transformations through just a transformation on the internal representation, not necessarily either the source code or the hardware which is going to implement that source code, but this intermediate illustration should make it obvious. First of all, what its origins were, where it came from, and also because of the simplification, what kind of hardware efficiency is obtained. I should be able to connect the dots, but we will talk about mostly the transformations that happen on the intermediate code. So, what happens before and what happens later, we can discuss if it is non-trivial, but in most of these cases hopefully the implications are obvious. Right. Here, what is the implication? Why is this a good idea to eliminate that operation 3 plus 4 and replace it by that partial computed result of 7? What is the point? How does it help?
Resources are being reduced.
Resources are being reduced. How?
We normally one cycle.
Yeah, so this 3 plus 4, if I had not simplified it, I would have scheduled that operation in one of the cycles, which means that it is taking a clock cycle. That resource that is performing the addition, that adder resource is blocked for this operation during that time period. Right. So, if we have enough information to actually evaluate it statically at compilation time, then the obvious question is why not, right. It will save something. So, that is the kind of simplification that is behind a number of these early optimizations. The argument is that this simplification makes sense irrespective of the details of the hardware architecture, irrespective of how many resources are available to you. Right. Makes sense means what? You might not always end up in a, let us say we are talking about time being saved, because part of the computation we have already done during the compilation time. Is time always saved as a result of this, or only sometimes?
Depends on the availability of number of adders.
It depends on the availability. Of course, in this particular example, it is obvious that we are saving time, but there is this question of should I be looking for, am I actually saving time, or when I find an opportunity for a constant folding, I just go ahead and do constant folding. Should always do, but does it always help?
No, so like let's say it's a synchronous circuit where like addition has to be performed in one cycle and then subtraction is in the next cycle. Then probably I'll be short of cycles and may result into some errors in the circuit.
Yeah, in this particular example, it is clear if these were single cycle operations, then instead of 2 cycles, I am taking 1 cycle. But
this linear dependency is not there.
Yeah, I may have a more complex. Let us say this is my graph, right, in which 3 plus 4 refers to just one part, but this on the right I had x, y variables, I can't get away from scheduling them. Then it is not clear that you are saving time, even if you discard this part of the computation, because there was enough information at compile time, you still need that much time, cycle 1, cycle 2 are still needed. The argument though is that the solution you expect would be better than or equal to the solution without doing constant folding. You might not be able to prove that it is always better, particularly we are doing it early on, right. At this stage we have not done a number of things, we have not done scheduling, for example. Right. So, without doing a schedule, it is hard to argue that this particular local transformation that you made is definitely going to save me time. Right. But similarly, in terms of area, from an area point of view, is it worth doing the constant folding operation?
Yes.
Yeah.
Always?
No.
Why no?
Sometimes I might anyway needs, let's say 3 adders, and in this case I am
we are talking about these 2 cycles, but maybe those 2 adders are there as my resources anyway. In some other cycle I am going to use 2 adders, right. So, then It is not clear that you are actually saving on the resources, but the general argument is that it may help, but it is hard to argue that it may make it worse. Some of the optimizations are of that nature, they are very interesting ones, and we should look at a few of those, but this kind of simplification can only lead in one direction. The other part of the discussion is how do you do constant folding. I should in order to implement this intuition, I have to write an algorithm for performing constant folding. Right. What would that algorithm be? Input to that algorithm is what? Is the representation, it is in the form of that control data flow graph. So, we understand what that looks like, and what I have here on the left a subgraph of the bigger structure. What is an algorithm for doing constant folding? Let us try to understand some of the issues involved by just writing a very simple algorithm. What is a very natural algorithm for doing constant folding?
First level would be just to parse the whole graph and look for the constants and remove that node and replace it with another constant node which is somehow.
So, let us traverse the graph one node at a time. Okay. The order is a little tricky, but let us say I just pick them in some order. I have for all nodes n, what should I do? So, I am let us say either here or one of these nodes. What should I do for each of the nodes? It can be a very simple strategy, right. So, for each of the nodes I should
look for incoming edges.
Yeah, look at all the incoming edges and check if all of them are constant. Remember, if one of them is constant, it does not necessarily help. If you have 1 plus x, constant folding does not immediately apply. But so, if I say if all operands of n are constant, then you just evaluate that node right there. You have enough information to perform the evaluation. Then we will say you evaluate, and I am just informally writing it. Obviously, all operands involves what kind of operation? This also may involve in the general case loop over all the incoming edges of that operation. But anyway, number of incoming edges for an operation may not be too many, maybe it is a binary operation, you have only 2 or max maybe 3, or not too many are there. So, I am leaving that detail out, but in the general case, depending on the way you have designed the graph, this may be actually a loop inside the outer loop. Just understand that in the general case it's you have a loop there, but a loop with not too many iterations is expected there. You evaluate, then after evaluation yes, there is a replacement that happens. You take part of the graph, right. Here we took a part of that graph and replaced it by some other graph. So, in the general case you are just replacing maybe it is n itself by the evaluated result. There is some patching of that graph that needs to be done. So, some edges have to be deleted, a node has to be deleted, and it is maybe replaced by a new node, all of which I am not writing in this algorithm, but at the high level that is what I would be doing. What else? After that? After that I just move to the next node, right. So, that is my action for one vertex, one node. If it turns out that all the operands are constant, then I can go ahead and do this constant folding. If not, then I just move to the next node. Okay. So, we can start off with an algorithm like this. Can we comment on its effectiveness? how good is it. These are called optimization passes. Each individual optimization that we perform may be called one pass through. This is a pass that we are doing over the entire graph, right. We are looking for all opportunities that exist for performing that optimization in a local sense, and we are performing it. So, an optimization pass is good if it can detect and act upon all the opportunities that are there in the user's design. Can we comment upon, is this good enough or it needs further improvement? Can you think of expressions that we write which in which it is clear when we look at it manually that there are some opportunities for folding constants, but this algorithm does not catch it?
Deciding on the direction in which we'll move in graph. So let's say I start from the top.
We haven't decided on the direction. Yeah. What? How does it help? Knowledge of the direction.
So it's more of like, let's say I have, how do I show?
If I have
You can draw the diagram.
From very bottom of the graph,
Right.
and then start folding from there, I may miss out one of the opportunity which could have been folded if I started in a sorted order.
Yes, I think both of you are talking about a similar limitation. Say I had this 3, 4, 5. That was my graph. It is obvious that there is an opportunity for folding out everything, my whole graph. But that algorithm, does it actually do that or not? No.
If we start with,
it depends on the order in which you process the nodes. If you start with that node and replace this by 7, then in a second phase you can replace the whole thing by just one result. On the other hand, if you start from here, then what happens? You actually fail. This condition does not hold because all the incoming edges are not constants. Therefore, this is not good enough. So, at this point we are just trying to identify what its weaknesses are. You could try and fix it, but this is one kind of weakness. What other kind of weakness would be there? Maybe before that, let us try to resolve. How do we fix this?
So we recursively, so when I start, so in this example I am correct. So now if I look at my, so the parent of this node, I see if my parent is already visited or processed by my algorithm. If it is not, we check for that first, if it can be optimized. If not, similar.
There are traversal orders of the graphs that we can follow to resolve situations like these. Let us say cycles are not there in this graph, which is okay, right? In our CDFG, the individual DFG, there are actually no cycles. So, this if we apply on an individual DFG, then somehow we should proceed from top to bottom and not from bottom to top. Intuitively, but the way to achieve that is this kind of orderings of the graph traversal will make sure that if there is a dependent node, that is what, there is a dependency in these two. So, if there is a dependent node, then the node that is dependent on some other node, waiting for a result from some other node, should be computed later, right. So, we should start from those nodes that have the least dependencies. If we do that, then we can resolve a situation like this. But that is just one limitation. Can we think of other examples that this algorithm is not good enough to detect here?
Sir, if from an upper block we have a computation which has variables but always returns in a constant. For example, if we have a multiplier as a block and we have 0 as one of the inputs and any variable as the other inputs. So the output will
Okay.
always be a constant.
So, this is actually yeah, one could call it as part of constant folding. The fact that you have some kind of operations in which the knowledge of one of the operands is enough for us to know what the result is. So, there you could think of a set of specific values that help in this kind of simplification. If you have one of the operands 0 to a multiplier, you know what the result is. Similarly, in this class you can think of a number of other simplifications. For addition, what rule can we use? These are like rules that one can actually specify to the system to aid in the simplification. For addition, what rule can you think of? For multiplication, it is this rule. If you have 0 and it is multiplied by x, the result is 0. This certainly helps in simplification. For addition, what kind of rules apply?
0 plus x is x.
Yeah, so all of those simplifications, so if I have some such thing and associated with it, there are a bunch of such rules you can think of. For every operation, you might come up with some such special cases that one can easily do an early lookup to see whether the situation is such that it permits the application of these rules of simplification. Any other kind of situation? We are trying to make that constant folding algorithm more and more aggressive. Right. So, we have already found some cases that I did not say how we adjust the algorithm, but it should be clear hopefully. What is the central traversal mechanism and processing each of the nodes, that does not change, you can still keep it the same thing, but the actions that you are performing inside can be more complex. You can look out for more patterns than just the simple one that we looked at. There are some other things that are also applicable. There is a complex expression. Could it be that you detect the application of some local constant folding opportunities that does not necessarily get addressed by our simple algorithm? Maybe we have fixed it for a simple expression, which is just one binary operator, say. But what if you had 10 different operands and a complex expression? The opportunities for optimization may lie buried in different parts of the expression. What is an example of that? In different parts, that for a single operation, when you look at both its operands, the folding opportunity does not apply, but we could do something to that expression to discover the opportunity for folding.
Breaking the operation into subparts.
Right, but what is, let us just start from an example. What kind of a pattern are we looking for?
So 2 plus x minus 5 if the
If I have an expression like this, minus 5, right. Do you see that the algorithm does not work? Because it leads to that kind of a graph, and obviously in both the nodes, both this and this, the simple rule that we have does not work. Of course, you can expand it to a more general expression in which constants are there, but they are not all nicely bunched together for us to discover, but the opportunity is still there, right. So, somewhere, so these are separated out in the expression, but the opportunity is there. It is just that that simple algorithm does not catch it. What can we do about this?
So the left to right assignment as to the graph reorder. I do not know the
Yeah,
but
you are on the right track. We have to restructure that graph in some way without changing the meaning of the expression, of course, but that restructuring might actually help. What we conceptually want to do is bring these constants closer in the graph, so that we detect an opportunity. Our basic algorithm need not change, right. Finally, we want to apply that same pattern search, which is that for an operation, do you find both its operand, all its operands constant. But we may need a pre-processing stage where these two are actually brought closer to each other. what could that be? What kind of, how can I restructure this graph so that the opportunity is more clear?
Why don't we do this when we are creating this DAG? Initially parsing the STO.
Actually, this transformation is done very early on, but what information do you have at the time that you are creating the DH?
So when I am creating for this expression, so a simple rule like, okay, first I'll take into the process the constants from the expression and then the variables. The graph will be created like 2, 5, right? So
The
when I'm
creation of that graph, even though it seems as though with an example you are thinking of a process that solves that particular example, but if we make it more complex, then in the general case there is a complex expression and there is an opportunity to do something, to combine something here with something that is there. You do need an algorithm that is general enough. Right. If it is simple enough, then we could do it during parsing, but this is a discussion that we did have during the parsing, which is if it is reasonably complex, then you do not want to burden the parsing process. Remember, during the parsing there is an elementary thing that is not known. Optimization opportunities are not known, they exist and so on, but what is the other very elementary thing that is not known during parsing? You do not know whether there is an error in the, there is a syntax error that is going to show up. Okay, then if it is going to show up, then you would rather flag it as early as possible and not really proceed to optimization steps. Right? Remember, optimizations are always considered a little optional. Certainly in early stages, as we are verifying our design for correctness, we are not yet bothered about optimization. We are first bothered about whether it is actually working okay or not. That is the reason why too much sophistication is typically not introduced into parsing and very early stage. But this, having said that, this is still very early stage that we are talking about. We have not done anything. We have only captured it in the representation, and all these analysis is happening on the representation. But every other step does come later. These are simplification steps that we start off with indeed. Okay, yeah.
For that argument that we don't want to load the initial step and we want to see if it is working correct, compiling out first.
Yeah.
So we can provide the optimization options. So for example, in typical GCCs you have optimization options with one UL.
Right.
So similarly in such front end.
But that does not change. Even to a synthesis tool, you can provide an optimization, levels of optimization like you would to a compiler. That does not affect parsing. That affects what subset of the available optimizations would be performed, but we still do not do it during parsing. But anyway, restructuring is easier said than done. How do you restructure?
Sir, can we try to change the, like if I have x minus 5 and if I make it minus 5 plus x and then I
yes. But how do you just first of all, getting back to the simple example, how do you restructure it in a way that we can discover the constant folding opportunity more easily? Two constants are there, you add 2 and you subtract 5. What is the simplification? It seems as though as a result of whatever we do, we should subtract 3 from this, but I should just be able to achieve that formally through some algorithm. Right. So, what restructuring can I do? It should be the output of a series of transformations on that structure, because that is my input graph.
Looking at example, one simple thing can be, so when I start parsing my graph, I look at my incoming edge. If any of the incoming edge is a constant, then I look at my children.
Oh, but you are talking about the algorithm. I have not got there. Just give me the restructured graph that will lead to a constant folding opportunity. Yeah. Why are you thinking so much? It's dangerous to try and impute complicated motives when somebody is asking a simple question. Is it good enough?
No, maybe you want to put 3 minus.
Oh, wait. Minus, but that comes later. First I have to restructure the graph and then apply my old algorithm, because that algorithm would work on this graph, right, because it has now found an operator for which all the operands are constants. This would lead to 3, the constant folding optimization we wanted to. But what is also being pointed out is that the subtraction operation can be a little tricky sometimes. For what reason? It does not have that associativity property. You cannot just interchange the order and expect everything to be fine. So, the suggestion was that you have anyway this is a constant that is being subtracted. So, you have this 2 x and you actually replace it with a plus, and that constant instead of 5 you just make it minus 5. It is an integer, and negative integers are fine. But then with this kind of a structure, if let us say all our nodes were plus operations, then it would be much easier. We do not have to worry about correctness, and we can try out many different structures, some of which might lead to that optimization. Yeah. So, this is just illustrating the intuition that there exists the opportunity for performing these kind of optimizations. Like I said, any restructuring of course has to maintain the correctness of the specification. You can't change the meaning of the statement. But how many such restructurings are possible? If you have one node, then how many possible structures are there? How many graph structures? We are saying that nodes are there, but the way they are connected is up to us. Let us say all the nodes are either variable nodes or constant nodes, or these operation nodes, and let us say for simplification they were all the same kind of operator, all of them are additions. Even then there would be a very large number of combinations, number of different graph structures which would be equivalent with respect to the functionality, but they would be different structurally. That number you can actually easily see will be exponential in the number of nodes. Right. Why is it exponential? You can take that as a homework problem, but it should be easy to see. Even if you fix the addition structure, operation structure, and you see that there are n slots, all of those inputs, all my variables, constants, and all of them can fit. You can see one ordering correspond to n slots that are there, n factorial orderings are there, right. So, it should be at least n factorial. All of them are not necessarily legal if you have other kinds of operations that are not associative and so on, but in general there would be a very large number of these restructurings. So, we need some simplification in that procedure also, knowing that restructurings are there. If I have 10 operands there in my expression, then I can't necessarily afford to try out all the restructurings and in the process find out which is the one that is applicable for constant folding. One kind of heuristic that is often performed is you have an expression of this nature, 2 plus x minus 5 plus y, some such expression is there. You try to push all the constants to one side of a larger expression. In the process you hope that you can discover as many possibilities for constant folding as possible. So, from here you can say 2 minus 5 plus 3, these we try to shift to one side, and the variables you keep to the other side. That might actually help us converge faster with respect to finding the opportunities for constant folding. This is not foolproof. The moment you have subtraction and other kinds of operations, you can't necessarily shift everything to one side, but it is a reasonable heuristic that is often used. So, anyway, that was just an illustration of what seems like a very obvious optimization from an intuition point of view, but to actually apply it aggressively you do need a little more careful thought in the algorithm. So, on one hand you would like to extract and operate upon as many such opportunities as are present in the code. On the other hand, you do need that algorithm to be scalable such that If the expression is large or the number of statements is large, then you still finish within a reasonable amount of time. Such a trade off is always there in any kind of optimization. This is just a simple optimization that illustrates that trade off. How much time you spend in discovering all the opportunities for optimization versus how good the quality of the optimization is.
So if the operator is fixed, then we can simply iterate through all the edges that we have, and every time we find a constant, we can give it to a queue or stack or something, and then we can create a graph from
If
there.
you have more information about the kind of expression it is, you can be more efficient with respect to evaluating it, of course, yes, but just that in the general case, I do not assume that operators are fixed or they have certain properties that allow any kind of reordering and so on. We discover that as we traverse the graph, and the algorithm should be such that it is able to handle all possibilities, all the operators it is able to handle in one integrated framework. So, yeah, that is what constant folding is about. Let us also take a look at a few other optimizations, not all of them to the same level of depth, but we will point out what the opportunities are. The other thing that happens is you may be needed to iterate over a set of optimizations. That should be clearer with the second one that we illustrate, second and third one. Let us introduce this other, from a control flow point of view, simple optimization called dead code elimination. Idea is you delete what you discover are redundant parts of the code. When can you assert that a code is redundant, some statement is redundant? There are a number of such opportunities, but the simple one here is that there is a control flow here, right? That second statement is actually taking you somewhere else. Right. So, because control flow is going to take you somewhere else, if it's this is part of a function and it is taking you to the end of the function, you can assert that this statement there will never be executed, right. You will never reach that statement. Since you cannot reach, why do not we just throw out that statement? What benefits are there, those are a different question, but at least one obvious benefit from a compiler's point of view is that it has simplified your CDFG. Right. Now, there are fewer nodes in the CDFG, and therefore, a number of other things that you do, there would be dependent on the complexity of the CDFG, the size of the CDFG in terms of edges, nodes and so on. From that point of view, at least it is worth performing the dead code elimination kind of optimizations. So, there are a number of such control structures which might lead to some statements becoming redundant. Break is a similar kind of a statement. So, return was taking us out of the function, break takes us out of a loop or something like that, and in that process it would be that maybe we can assert that some particular statements become redundant. Of course, as we make these decisions, we do need to take care that it is not possible for us to jump from some other part of the code to that statement that we are about to drop. That check does need to be made. How do you make that check? Often compilers do the following. They look at whether there is a label that you have attached to some statement. If you have attached it, it may mean that you have a jump statement from some other part of the code to that label. The definition of the basic block, which we defined as sequence of instructions with one entry point and one exit point, that is influenced by the presence of labels, because it may indicate an alternative entry point. Right. So, you do need to check to make sure that it is not possible to enter that in some other way. As long as that is there, you could do this kind of redundancy removal. So, from a control flow point of view, this is a simplification, and once you have identified it, it should be clear how to simplify it. The other kind of simplification is the following. This kind of a statement has some redundancy in it. What is the redundancy? That can be anticipated at the compile time. Where is the redundancy? That condition can be pre-computed. Right. Since it can be computed statically, I already know whether I will be entering this branch or this branch. There is nothing dynamic about it. Even if it is part of a loop, every time I come to this if statement, in fact, I would never reach that part of it. So, I could in fact throw out the complete conditional and just replace it by the statement or list of statements that are going to be executed. So, this is a generalization of the dead code elimination. So, part of the graph becomes dead code. Let me conclude this. By itself, it is not clear that it is dead code. On this particular example, you have to do one other thing before you conclude that some code is dead. What is it?
The first optimization way.
Yes, we have to perform a constant folding. I have to recognize that there is an opportunity for constant folding, and this 1 equal to 0 translates to false. That is the simplification intermediate step that was not shown here, and then you say that if false, then something else, therefore, you can perform that elimination. Right. So, that implicit constant folding opportunity is there. It has to be performed first. If you directly start with dead code elimination, you will not detect it because it is not false. It is just you see an equality operator, and if your algorithm was coded as if it is if I know it is true or false, then I proceed, otherwise I will discard it, then you might not discover it. Yeah.
If I'm writing to a signal but I'm not reading that signal anywhere in the code, so that will be a part of dead code elimination.
If you are writing to a signal like that, but that signal is not used anywhere in the code, is it dead code? So, this is the architecture. The architecture has a signal, or there is a port called A.
Sir, it can be both, like if my two entities are connected and from one entity
Okay, fine.
there is an output.
Fine. So, let us have a port. So, this A is actually a port for us, and I did A equals 1, and I have some other things, and that is my model. Is that statement redundant?
But if it's an output port, then it's an input port for any other entity, and I'm
Right.
not reading that input port anywhere in that particular application.
It is an output port from here, and it does form an input port to some other entity, and
I'm not reading that input port, so I'm not using.
in that other entity you are not using it in any way. Therefore, can you throw out this assignment? Why? Should it show up in a waveform that we plot?
Yes.
The value of 1 being assigned to A should show up if the simulator gives me a way of plotting all the signals, all the ports, right? Should it show up? It should have the right values should show up.
So simulation it makes sense, but synthesis after I make my
Okay, so in simulation, so I can't throw it out for the simulation. For synthesis, as you are generating hardware for these modules, would you assign the one value to the port or not?
So we will assign.
You will assign. Why?
So we cannot leave the port open of any input even if it is not used. It will be floating. I mean, it will cause some problems.
Floating. So
From a
port
hardware
optimization is
perspective.
not.
Well-
it is optional. It can't be.
Say I had B plus C, would you still perform the addition? There is a methodology issue that the port has to be connected to something, therefore, maybe I just connect it, but should I perform that operation? Knowing that ultimately that result is not being read by anyone, should I perform it or not? From an overall methodology point of view, we can't throw it out for the following reason. You may not have, as you are synthesizing a piece of specification, you actually may not have enough information about all the contexts in which that design is going to be used. It seems as though here we know everything about it, not only about that particular entity, but also that it is part of a bigger system about which we are assuming full knowledge, and during that synthesis we have not only full visibility into that entity, but also into that other entity in order to conclude that it is useless assignment. All of those assumptions often we do not make as we perform synthesis, nor as we perform compilation. Remember, as you are compiling a large piece of code, the code might be separated out into multiple files. As you analyze one function, you have no way of knowing whether that function is going to be called from some other file or not. We process things one translation unit at a time, and it is often that translation unit is a file. And in fact, the compiler generates its output on a per file basis, might not assume any knowledge about all the contexts in which the functions that are visible externally in that file are used. In fact, that is considered good design practice, right, to not assume anything about how somebody is going to use. If you are exporting something, then you assume that it will be used in whatever way. This is that kind of a situation. The equivalent of the file in software here is that entity. So, within the entity we may perform all the aggressive optimizations. Across entities, sometimes we could, if we flatten the whole structure and optimize it together. But if the designs that we are producing are on a per entity, you are synthesizing things one entity at a time, which might be the more common situation, then you do not assume about who is connected and how they are going to be using it.
In a typical ASIC design process, we explicitly tell our synthesis tool to preserve hierarchies, and there the port optimizations do not happen. But where we say flatten, as you said, do not preserve the hierarchy.
It might, in conclusion, we might actually leave it as an option to the tool to either make that assumption or not make that assumption. But it often would be that if we want to reuse the design for anything else, then we would like to preserve it. But the option might be there for us. Okay, move on to a related transformation called constant propagation. That is,
all these optimization tricks that we are talking about, they have an inherent dependence in terms of sequence in which they can be executed.
There is a
and
dependence
they can give
on the
different
sequence.
benefit. Right. So, for example, without constant propagation, we may not know that if 1 equal to 0, there is a way. I mean, if we first propagate the constant.
So, we are pointing these out as independent optimizations, but this is mostly from an engineering simplicity point of view and also from the point of view of presentation. What is the right ordering to use? What is the optimal ordering for a set of compiler optimizations? It is a difficult problem, NP hard problem.
What if it was a signal in the same problem? I mean, we discussed it for a code. If it was a signal, it would have been redundant and part of that code.
No, so this decision has to be first made. As we write this kind of code, we are assuming that these are all variables with local scope. You can do whatever you want. Throwing out something is okay. Often throwing out something is not okay because of reasons like that. Signal assignment, you may want to preserve the history. A simulator definitely is obliged to preserve the history of a signal assignment all through the simulation, even if the only assignment happened only at time 0, then too we are obliged to preserve it. Synthesis, we looked at this example of whether we should keep it or not, but for signals and ports we have to define at a higher level of abstraction whether we should optimize them. Nevertheless, even the optimization opportunities exist, like all of these things can still be optimized. The RHS of a signal, all of these opportunities do apply there, but whether assignments can be completely thrown away or not is a more complex question. Signal assignments, we may not want to throw it away. But much of these discussions we can assume that these are variables. As you can see, the syntax here used is a little loose deliberately because I do not want to make language specific assumptions there, but we can assume that these are variables. A different illustration, constant propagation refers to propagation of the knowledge of a value of a variable to its use, even though in the context of its specified use it is actually a variable. You may actually be able to establish that the value of that variable at the time that it is used is already known and it is known to be a constant. Okay, so that is what is called constant propagation. If I knew that this 1 that I have here is what flows into x, and only that 1 is going to be flowing, then I can replace it by something like this, where I say the x which was a variable is replaced by a constant. Why do I do that? How does it help?
Then we can use code by code
Dead code and dead code.
Both the other optimizations that we talked about. First, the constant folding is applicable. It is discoverable only if you perform the constant propagation, otherwise it is not even applicable. Okay. Then once constant folding application is known, there is also a further dead code elimination. You can see that these optimizations are interdependent. One might help the other. Practically, it might happen that we arrange these in the form of some sequence, and you iterate upon that sequence until there is no further improvement that is visible. This is a practical example. Compilers typically do this, optimizers do this. You perform one set of optimizations, you iterate over the same set again, maybe they create another set of opportunities for optimization. You go over it again. So, hopefully, this does not take too many iterations to converge. Convergence just means that I do not identify any more opportunities for optimization. Yeah.
What if this x is a signal which is used in some other process? So then we can't do this?
What if x was a signal that is visible in some other process? Then it is still valid or not valid? Replacing this code by this code is valid or not? Throwing out that assignment is not valid, but after that the rest of it is actually valid. The propagation is not an issue. In fact, I have simplified the discussion a little bit here. The propagation just refers to taking the value, recognizing that this is the value and substituting that value for the constant. That is all that we do when we say propagation. Throwing that assignment out is part of some other optimization. I have just combined them in the interest of simplification, but that could be part of a different argument whether we should be throwing out or not. If nobody needs it, then we throw it out. If somebody needs it, then we keep it, but that does not invalidate the rest of the optimization, which is the application of the constant folding, application of the dead code. These are still applicable. Of course, through all this you remember that in the signal assignment, when you do x equals 1, it is not immediately visible in the same delta. Therefore, that new value, if this was a signal assignment, it would not reach the x equals 0. Is that clear? I have a x, if I had this x equals 1, and immediately after if x equal to, so this is VSDL, so if some such statement, then that new value does not reach this because we did not have an intervening weight or something like that. You have to wait until the next delta, and therefore, that does introduce some complication here. Our rules are still the same, which is that this x, when we say it actually uses the old value, then the assignment is made to some other value. Remember, it is the way to understand signal assignments we said was that pretend that the assignment is happening to a temporary variable. Since it is happening to a temporary variable, it is not visible to that immediately following statement and cannot be optimized away. The constant propagation does not work. Let us talk about a few other such simple transformations. Strength reduction refers to finding ways of replacing an expensive operation, however we define expense in terms of area or power or time, with a cheaper operation that does the same thing. Example would be that you have a multiplication with a number that is a power of 2. This is an integer and this is a multiplication with a power of 2. I have with me a set of rules that tell me that these two are actually equivalent. One can do a local replacement of a multiplication with a left shift operation that does the same thing. Would it make sense? Why are we saying this is a cheaper thing to do? How do you do multiplication operation? You need a multiplier, right? If you do left shift, A is stored in a register, say. How do you do left shift by 4?
of multiplication.
Yeah, so let us say I have a 5 bit register, A is here, and I instead of 5 bit, let me make it some more bits, 8 bits. How do you do left shift by 4? So, somehow it seems that I should take these 4 bits, or at least I can assume that there are these 4 zeros out there, and it depends on what it is that I am assigning it to, but it could be that if I am assigning it to a 12 bit number, then that is what I have. Right. So, what hardware was needed to perform the left shift? Is it a shift register that is needed? Can you do with something else that is simpler than a shift register? This is my A and this is my Y, which is A shifted left 4 bits. You could use a shift register, but what else could you use? Where is the shift register? Where should I put my shift register here?
So in case of shift operation, we do shift for only the carry flag. So the bit which will be shifted goes to the carry, and the other 8 bits are like same. That means like throwing the 0 from the right side. So again and again 4 times we will throw the 0 to the register. So the register will be same of the 8 bits only. And the carry
whether it is 8 bits or not, it depends on what I did not say what is the type of A, what is the type of B. Let us say we had allocated 8 bits for A and 12 bits for Y. Then these 8 bits of A still become the higher 8 bits for Y, but the lower 4 bits can become 0, or whatever the algorithm is, I can perform the appropriate manipulation in the way I pick up the input bits. But what hardware is needed and why? Y needs to be stored here. I need if this Y is to go into a register, then this is a 12 bit register that is needed. So, where should I put the shift register? You remember, if Y was 8 bits, then what should we do? An algorithm is clearly there. What the shifting by 4 bits or 3 bits or whatever it is. Just trying to find out what is the hardware. So, that we have to be able to argue, when I say cheaper, I have to have a hardware structure in mind, right. So, that I can say it is cheaper than a multiplier, right. So, what hardware are we talking about here?
So if Y is of 12 bits, we don't need a shift register because we can just extract the last 8 bits.
Yeah.
So we don't need as such.
So, there is no hardware, this is only an interconnection. That should be understood. There is actually nothing, there is no operation there, it is just a matter of me picking up the right bits from somewhere. I may need to handle the MSB bit, where if there is a sign bit or whatever, I do need to worry about it, but there is no shifter that is obviously implied by an operation like a left shift or a right shift. A shifter circuit, in general, you have to instantiate that when? For what kind of expression will you actually need to instantiate a shift circuit? Yes, if I had a left shifted by x, then you need a proper shifter circuit, because only at runtime you know how much to shift it by. So, the circuit is more complex. Since it is complex, you have to schedule that operation, and that takes some time, it takes some area and so on. But this particular kind of a class of operations, which is just multiplication by a constant translating to a shifting by a constant, the hardware required is trivially small. Remember, there is a power related argument in these optimizations that sometimes we overlook. So, one argument, counter argument could be, let us say you already have multiplier as a resource.
Yes, that's what
right. Suppose you already had that multiplier because you needed it for something else, then is it still a good idea to perform this or not, since from a you are not saving area, at least component area you are not saving because that multiplier is already there. But in spite of that, it might make sense. Well, I have to argue area, if it is just component area I am worried about, perhaps it is the same, but there might be other benefits. There might be delay related benefits because this is a much faster thing, but also there could be power related benefits, because if you were to do that multiplication to perform multiplication by 16 as opposed to just extracting the bits to perform multiplication by 16, the power consumption might be very different in both.
Let's say if I have to multiply with some number, let's say a into 6, then I will need a subtraction also, right? So I'll,
If you had this kind of a multiplication which is not a power of 2, nevertheless is realizable in terms of an adder would be enough to perform that kind of multiplication. You are right. So, I should be looking for such opportunities. I take that constant, this is a constant, so I can do a lot of things, a lot of static analysis could be done to find out what kind of hardware do I really need, what is the cheapest hardware with which I can perform that computation. So, I could actually realize this in terms of something like this, right, one shift by 2 and one shift by 1, which would translate to multiplication by 4 and multiplication by 2, and essentially I need only one adder to do this. So, yes, I should be looking out for such opportunities. The generalization of that is something like you have a set of variables, a set of constants. This happens in certain DSP kind of computations. You have constant coefficients with which you multiply variable data. Right. So, several such multiplications are there. What is the best circuit to realize that set of multiplications, all of which are of this nature, a variable multiplied by a constant. The default one would be if you just had a multiplier for each one of them, or you have one multiplier and you sequence all the operations over that multiplier, but these other interesting solutions might be there. It's expected that a synthesis tool is smart enough to do some little bit of exploration to find out what is the best way to realize a circuit. So, when you have constants like this, you do have such opportunities that you can explore.
So, in this case
Yeah.
particularly,
Yeah.
it is assumed that multiplication is more than 2 cycles.
It is assumed that multiplication is more than 2 cycles.
Or
Why?
more than 1 cycle.
Why?
The next statement, should it take,
The transformation is valid anyway. Right? We have to argue whether it is efficient or not. Are you saying that it is efficient only if the multiplication takes more?
because
Why?
the next statement takes at least 2 cycles, the shift operation.
This statement takes how many cycles? I have to first define what is the delay of all my operations, but what do you suggest is the time required to do that computation? Adder takes 1 cycle, let us assume. What should we assume about the time required for the shift? Yeah, we should assume it is 0. Well, it is not actually 0 because there are wires and so on, but from a component delay point of view, we are saying it does not require any component. It is a matter of us just taking the right bits from here, one set of bits. So, I have my A. Shift left by 2 means that okay, this is one operand where these are zeros, and the other operand is shift left by 1, which is right here. And make that 0, that is my other operand, and so as of now I have not taken any time, right. There is no gate that was required to derive this. After that I have to do an addition, that is what it is.
So, the registers are usually reused. In this case, the interconnection to happen and register to get loaded will take the interconnection part, which is
Where is the register?
the A.
Which register? This one,
Yes.
right. A is stored in a register, right.
No, after the shifting.
After the shifting, is there a need to store these intermediate values in a register?
To feed it to the adder,
Why?
You will have a dedicated adder just for this. Given a reasonable set of data flow, in that sense, would such transformation make sense? I mean, if
Okay, so let's go to the bigger problem later on, but let's just concentrate on this small problem yet. Question is, do I need storage for A shifted by 2 and A shifted by 1, or can I just take directly, I had my A and I had my adder, this is my adder circuit, and essentially I had 2 inputs there, that somehow this was this had 2 more zeros, and it is actually the same thing that is going here with the addition of another 0. Is this a valid circuit or not? It is a combinational circuit so far. I did not store these in any way. In fact, I had these 5 bits that were coming from A. Instead of that, I have 2 more bits that I have just added as inputs to the adder. Here it is 1 more. Is this a valid circuit? As of now, it is valid. Okay. So, when does it become not valid? So, suppose I had that adder was reused in some other cycle to do something else, not this particular addition. That will lead to us placing a mux here and a mux there. So, the second operand comes from some other part of the design. This is actually no different from the standard resource allocation that we have already talked about. As of now, unless I am going to need that 4A, or well, it is hard to argue that I need it in a way that if A is still there, then 4A can still be derived, or 2A can still be derived, 8A can still be derived. If I have reused that register for A in the meantime, that decision as of now we have not taken. Remember, as we are doing these operations here, high level transformations, we have not gone through all the synthesis steps of scheduling and resource allocation and register allocation and so on. So, unless I have lost that space for storing A itself, I can certainly derive A shifted by a constant number of bits whenever I need it. But it could be that at some time 4A is what I am storing, but A is not needed. So, let us say I reuse that register for something else, then maybe 4A is needed later on, and I need to store that value that was derived here, right, 4A and 2A. But it is often possible to do all this in just a simple combinational circuit that does not require additional storage. You can easily identify a subset of these operations for which there would be one default way of realizing them. Modulo division is also a similar example. The default one would be performing division and getting the quotient and the remainder, but it could be that often if the other operator there for the modulo is a power of 2, then of course I can realize it in a very simple way. What would that be? So, A mod 8 can be simplified when it comes to hardware realization as what?
Taking the last LSBs, 3 LSBs.
Yeah. So, A mod 8 would be, you just take this the 3 LSB bits, it is what is called a part select. We can include a dummy operation like a part select. It happens in 0 time as far as gate delay is concerned, for the same reason that the shift operation by a constant also happens in 0 time. So, strength reduction means that we have moved from a more complex operation to a simpler realization of that same operation. And there are some obvious benefits there, because the hardware would be simpler, which means that usually there would be an area benefit, there would also be a performance or a power benefit. Most of these optimizations that we are talking about at this stage belong to that class where we can argue that it makes sense to perform that optimization, even though we do not know a lot of details of what is coming up. Proper synthesis has not started yet, like what the resource constraints are, all of these things are not known, scheduling and all of those steps are not performed yet. Yet we can argue that a certain set of optimizations actually make sense. These are the class of optimizations that somehow lead towards simplicity. That simplicity it makes sense to argue about, even if for example, you do not know anything about the target architecture, whether it is an ASIC, whether it is an FPGA, whether it is a processor, all of these things usually can be ignored. The target architectures can be ignored for most of these optimizations. Some of them are interesting because they may represent trade offs, but often the simplification operations make sense to move in that direction. Remember that they may or may not result in improvement all the time, that does have a dependence on how you realize it, but it will not be worse, it would usually be better than or equal to. Yeah, let us stop here.